So hello everyone, myself Mohit and I'm recording this walkthrough on the behalf of our group to demonstrate our project Mini-Kubernetes or Mini-K8s. We wanted to deeply understand how massive distributed systems like Kubernetes actually work through the hood, so our team built this distributed scheduler from scratch in Go. So actually this Mini-Kubernetes or Mini-K8s featured a centralized control plane and distributed worker nodes that executes the real Docker containers and a Postgres database for the state management. And there is an interactive CLI tool through which we can send the HTTP request to our core architecture. So actually in this demonstration, I will tell you about our core architecture, show how our system schedules the task intelligently and demonstrate how it handles the self-healing when a node crashes. So now let's start our demonstration. For that we have to go in our terminals, and this is the terminal command, and I have to run the docker compose file build one. And before running the docker compose build, we have to ensure that docker engine is already running. So inside the docker desktop app we can see that our engine is running, so we can run that command. So after running that command, I will explain what this command means. So we are using a standard Docker Compose to build a spin up in our entire infrastructure locally right here in the foreground. Watching this in the live logs, you can see that it is spinning up our Postgres database, and as you can see that it is a Postgres database spinned up our central scheduler API and the three worker nodes and our Prometheus Grafana observability stack all at the once. So as you can see, all our infrastructure is up right now. Let's verify that our nodes are communicating properly or not using our CLI. So this is a custom made CLI that we have made. Its name is the Mini-K8s, and this is the command line interface for the interacting with Mini-K8s control pane. It uses to inspect the cluster state, submit tasks and jobs, and manage the namespace services secrets and troubleshoot what is the scheduler is doing. These are the available commands for that. Now we have to see that our nodes are there or not in the system. So this is the command for checking the nodes. After running that command, so this command uses a custom CLI tool emits. We're parsing the URL to point it specifically at our local control plane API and calling the get nodes to fetch the live cluster state directly from the Postgres. As you can see on the screen, our three worker nodes successfully registered in the scheduler. These are constantly sending HTTP heartbeats in the background, reporting their live CPU and memory usage. You can notice that there is a reliability score here. This gradually increases as our nodes proves they are stable to the control plane. So now coming to the next part. So as we can see that the worker nodes are working perfectly fine, and now we can submit a task inside this worker nodes, and we can put the task in the worker node using this command. I will explain this what this command does. So we are hitting the control plane API on the port 8080 and telling it to schedule a brand new task. The positional argument alpine latest proof that we can dynamically pull and execute any docker image in our cluster. We also pass a command flag to execute a 60-second sleep. So let's start it. So as you can see that task is submitted. So what happens, so as you can see that it is executed. So what happens is that the moment it hits the API, our mini K8s use a filter score band algorithm. It first filter out the nodes lacking enough CPU or memory. It then scores the CPU remaining nodes based on their reliability rating, available resources. So finally it binds the task to the absolute best node. So this is the result. Now we can see that it's working or not, or like by inspecting the by get task command. So this is the get task command. This command queries the control planes for all active tasks. So currently, as you can see, that is shown as the failed one. We can put in any another task inside it. So see running or not. So as you can see, that second task is running. The transition can be failed, running, or pending. This schedules determine exactly the worker can be best suited for it. It currently executing the image live on the worker Docker. Let's see that it's working fine or not in the Docker. So we have to go into the Docker. As you can see in the Docker desktop app, all the things are running perfectly fine. Our deployment schedules like Postgres 1, Scheduler 1, Grafana, Prometheus, and all the three worker nodes are perfectly fine. So now next part is about real-time observability. So to operate a cluster effectively, you need visibility. So our group embedded a Prometheus collector directly into the scheduler internal loop. Let's look back into the Grafana dashboard. First, we have to go into the Chrome and go to the localhost, localhost 3000. So it opens the dashboard. As you can see here, this is our Mini-K8s and Mini-8 cluster. These are the all the things, as you can see here: average node reliability, schedules, and the fragmentation, backing waste, scheduler latency. So the dashboard is directly entered by the data the worker transmitted during the heartbeats. We can visually track the cluster CPU, memory utilization, scheduler latencies, and node request. Everything updates in the real time, giving on the computer visibility on our environment. We can just reload it and it's just show real time data inside it. So what happening is like a true distributed system that has survived hardware failures. I am going to simulate a sudden catastrophic node crash right now to test our fault tolerance. So let's stop the worker on the bash and see that what happens inside that. So this is the let's take the command. uh, this is the stop worker node on the one. So let's put this command inside here. So what this command does is like by running the by what this command does is like it stop the worker node. uh, it's as you can see that is completely executed, and container deployment worker node where one is stopped. So what we have to do is like next put the next command here, that is the get nodes command, uh, to verify that there is a worker node here or not. So only worker 1 is down, and worker 2 and 3 is ready. So we can see that we can see that our scheduler failure detector immediately notice worker 1 has stopped sending heartbeats. It automatically marks the node status is down and its reliability score is plummeting. But what happened, our task that we are running on the task worker 1, that is here. So let's see that the task thing using this. So as you can see, the task is also failed. So now we can run a task one more time. Basically, our cluster maintains the state centrally. Our failure data loops identify the orphan workloads. It automatically requit them, and our scheduler gracefully reassign that to the healthy worker nodes that are still online. So as you can see that previously there are also field node, and currently today's field node, because their attempt counts is 1 2 3. This is a purposeful demonstration. The image is submitted purposefully. It throws a hard kernel error. Exit code 137. This beautifully showcases our handling capability logic. Not only what the cluster rescues tasks from dead hardware, but also tries from the workload level crashes in the real time, capping which capping the retries to prevent infinite crashes loops. So we put all the things together in our front end also. So we can run the front end using this command. So this is the front end command, which points our dashboard to the scheduler API and completes a map to the cluster in one view. We can open that inside our browser itself. So this is the thing we in the port 14173. We can connect. So in this front end, we can put our local host URL for the scheduler API, that is the on 8080 port. We can connect to it. Is already connected to the localhost 800 port, and we can see that there's currently 3 nodes and 2 are ready. And because one is already down, and there is no currently no running a pending task and no jobs and services, we can also make jobs inside our systems. So there's a as you can see, 2 stars recently failed. There's a completely insights of it, and we can filter out our namespaces or task schedules, and the current live info about worker 1, worker 2, worker 3s, and we can show the live workload queues inside it. So this is the way like assignment need. We have professional visualization for their distributed system architecture. So to wrap up, our group successfully engineered an environment with dynamically resource provisioning, intelligent scheduling, full stack observability, and distributed fault tolerance. Working on the Mini-K8s taught our team highly valuable reasons or lessons in concurrencies and system architecture. So thank you for the taking your time to watch our demonstration. Thank you.